Hi, and welcome to our talk on YAHPO, an efficient multi-objective multi-fidelity benchmark for HPO. This is joint work with Lennart Schneider, Julia Moosbauer, Martin Binder, and Bernd Bischel. So what is YAHPO and why should I use it? YAHPO proposes a suite of surrogate-based HPO benchmarks. All in all, it has around 700 benchmark instances. It includes many interesting problems, such as single and multi-learner search spaces, as well as hierarchical but also continuous search spaces. All problems in YAHPO are multi-objective and multi-fidelity. This means they can be evaluated at varying fidelity steps and all have multiple objectives that can be evaluated. Through the use of surrogates, we obtain really fast evaluations. So typically a random search with around 300 evaluations takes 0.4 seconds and around 100 megabytes of memory. Surrogate predictions are also highly accurate and they approximate the real response surface with high fidelity. All surrogates also include runtime prediction to simulate real-time evaluation. We furthermore propose a carefully selected subset of around 20 instances for both single-objective and multi-objective optimization, together with various baselines for your benchmarks. So why surrogates? Tabular benchmarks discretize the search space, so they can only contain points that have been evaluated previously. This changes the optimization problem. For example, infill optimization during Bayesian optimization becomes way easier because we can evaluate only a fixed set of points. We conduct a small experiment to investigate the effect of this discretization on the current 2D synthetic benchmark function. For this experiment, we use a tabular benchmark with 10,000 points, a surrogate benchmark trained on the same 10,000 points, and the real function evaluation, and compare them across 8 optimizers. On the right hand side, we can see the result of our small experiment. We plot the mean rank of our 8 optimizers against the cumulative budget. We can see that the surrogate benchmark tracks the real benchmark way closer than the tabular benchmarks. So there seems to be some effect due to the discretization. We also evaluate the quality for our surrogates using multiple metrics. Surrogates achieve Spearman's rho between 0.73 and 0.98 on almost all tasks. And also the learning curves are qualitatively very similar to the real learning curves. As we can see on the right hand side, where the solid line is our surrogate prediction and the dashed line are real evaluations. We can now also evaluate our surrogates at arbitrary fidelities. So what's the secret sauce behind our surrogate models? We develop a specialized tabular neural network architecture that allows us to model all metrics across all tasks in a single neural network. Inputs and outputs are custom scaled before entering or exiting the neural network, for example by log scaling continuous hyperparameters. For categorical hyperparameters and as well as the task ID, we use entity embeddings. We then pass this on to a tabular ResNet, which then predicts scaled response variables such as, for example, accuracy or log loss or the time it took to train the model. We then compress this end-to-end trained neural network using ONNX, which allows us high throughput and portability, as ONNX models can be used system independent. In order to fit such neural network models across all benchmark problems included in YAHPO, we develop a tiny AutoML system that allows training surrogates. So if you have your own data, feel free to use our tiny AutoML system. So what kind of benchmarks does YAHPO include? And what kind of benchmarks can I run using YAHPO? It includes search spaces for machine learning algorithms such as ElasticNet, decision trees, support vector machines, random forest, approximate k-nearest neighbors, and XGBoost. Either predicting memory consumption as an additional objective, this is available across more than 100 datasets, or interpretability metrics as an additional objective. This is only available across 4 datasets. Additional search spaces include the LC-Bench search space, which is a search space for a multi-layer perceptron, available across 34 datasets, and the NAS-Bench 301, a neural architecture search space. We furthermore include an AutoML search base, which allows to search across multiple estimators and their hyperparameters for the RBV2 and IAML scenarios. To give you a better picture of what kind of research questions you can answer, we answer two simple research questions. First, in the single objective case, do multi-fidelity HPO methods improve over full fidelity methods? We compare random search, hyperband, differential evolution hyperband, Optuna, SMAC, Bob, and SMAC hyperband. The figure below shows the results of our experiment. After 25% of our optimization budget, Optuna, Bob, SMAC hyperband, and hyperband significantly improve over SMAC and random search. So it seems that at least for smaller budgets, multi-fidelity methods improve over full fidelity methods. This picture changes when we allow for high optimization budgets. In this case, SMAC still improves over other baselines such as Bob, Deb, hyperband, and random search. So for higher budgets, it seems that this is not necessarily the case. As a second research question, we want to answer whether multi-objective HPO methods improve over random search. In order to evaluate this, we compare several multi-objective baselines against random search and random search with a quadrupled budget as a strong baseline. After 25% of the optimization budget, we can see that random search with quadrupled budget actually outperforms all other methods, and there's no significant difference between random search and the other methods, such as MEGO and PAR-EGO. After the full budget, we can see that several methods, such as MEGO, PAR-EGO, and mixed integer evolutionary strategies are on par with random search and significantly outperform random search. In future work, we would like to simulate real-time, asynchronous, and parallel HPO. Furthermore, we would like to give users the possibility to better investigate noisy aspects of hyperparameter optimization. This is already available to some degree, but we would really like to look into it in more detail. Furthermore, we are always happy to include more and more interesting multi-objective benchmarks. So to finish, we would like to ask you, what would make YAHPO more useful for you, and which kind of research questions would you be interested in answering? We can now investigate dozens of research questions in a very short time due to the fast inference of our surrogates.